Okay. Reminder that starting today you have quizzes after the lecture, and they are due right before lecture on Thursday. So they'll due at 12:30 p.m. and they're just a quick review over the material that we cover in the lecture and in the book. They should take you no more than 20 minutes. In fact, I think I put a limit on that because I want you to move through it, get on to other things. Also remember, you need to do those participation activities before class as well. So generally from now on, you'll have 2 tasks to complete, at least through the month of January. You'll have 2 tasks to complete before each class. 1, the quiz. 2, the participation activities. Now, on Thursdays, the quizzes are due within 48 hours. So the quizzes are due on Saturday. Participation activities are always due right before class. Okay, so questions about that? Okay, so today we are going to be looking at some of the differences between the basic control structures and arrays in C++ and Java. So for the most part, as I said last time, the syntax, the control syntax is the same. The syntax for variable declarations, assignment statements, comparisons, if-then-else statements, for loops, while loops, do-while loops, they're pretty much exactly the same between C++ and Java. I shouldn't say pretty much, they are exactly the same. The only difference that I can think of in types is that in C++ you declare booleans as bool, and in Java you declare them as boolean. And Java has a few specific, it is very clear in the standard about its types. So if you look at the types, there are 4 different kinds of integers. So if you want an 8-bit integer, you declare something as a byte. If you want a 16-bit integer, you declare it as a short. You want a 32-bit integer, you declare it as an int. You want a 64-bit integer, you declare it as a long. And with the floating points, you want a float, you get 32 bits. You declare it as a double, you get 64 bits. The C++ implementations aren't as consistent on this. You might think you're getting, say, 32 bits with an int and actually get 64 bits. You might think you're getting 16 bits with a short and you get 32. But with Java, it's pretty strict in the standard, so you can be pretty confident that these are the amount of storage you will get for the various ones. So that's pretty much the only difference as far as the types go. So what I want to do is talk then about the differences. The first one is a difference between your .h files that you had in C++ and what you have in Java. Then we're going to look at some of the slight differences between strings. Then we will look at some of the differences between arrays and memory management. Okay, so that will pretty much be, and we'll also look at enumerated types, which are a lot more robust and feature-laden in Java. Okay, so the final thing that I did not get to is that in the runtime environment that we have with Java, Java doesn't create a monolithic object file or executable the way C++ does. Instead, it dynamically loads classes on demand. So when you type Java foo, it loads that class, starts executing main. It may well start in an anticipatory fashion loading classes, so there's no delay when you access a class that has not yet been loaded. But the idea with Java originally was that it was coming in over the internet. The internet was very slow when Java was introduced, only about 56K bits per second. And if you had to wait for an entire executable to arrive before the program started executing, that was pretty slow. So instead, they said, okay, we will start executing as soon as we have the initial class, and then we'll keep streaming classes down over the internet in the background as we run the program. Hopefully by the time we access a class, it's already been loaded. If not, we'll temporarily suspend the execution of the program until that class is loaded. So at any rate, that model continues to this day. You don't have a single object file in Java. Instead, you have a series of individual .class files. Just like in C++, you may have a series of .o files, but they're not all crunched together in Java. They always remain separate. And then, as I said, when you access a class for the first time, if it's not yet been loaded, Java will not terminate. It will stop execution of your program, load that class file, and then continue. Okay. So the other thing is that Java decided that this notion of separating .cpp and .h files was inconvenient and somewhat hard for programmers to deal with while they were programming. The API would be in the .h file. The actual code for implementing the functions would be in a .cpp file. The Java developers decided everything would go in one file. So in Java, when you declare a class, you not only, if you have like class foo, not only do you declare the method, like say int get x, but you also in Java include the function body there. So in Java, everything is in one file. The class declaration and all of the function methods are included in the same file. You don't put them in two separate files. Okay, so no .h files in Java. Everything goes in the same file. So that's another important difference between Java and C++. Okay, so first big difference in things between C++ and Java comes in their handling of strings. So both C++ and Java have strings as objects. Okay, so that's not the difference. Remember, in Java, you need to capitalize the string class. So in Java, by convention, all object classes start with a capital letter. You should adopt that convention too. So if in doubt, if something is a class, the first letter is capitalized, essentially camel case. If you haven't heard that term before, it simply means this is also camel case. So in Java, you don't separate words with a dash or an underscore. You simply run everything together, and where there would be a separation, you capitalize that word. Okay, that's called camel case. Okay, you don't use underscores. It's a style thing. It's not required by the compiler. It's just that's what has happened. Okay, so the string class. First thing about strings, they're immutable. Once you've created a string, you cannot modify it. So remember in C++, if you have a string, say name equals Brad, and now you say name equals Nils. If you're wondering why that unusual name, he's my brother. So you'll see, get to know my wife's name, my dog's name, my brother's name while we're at it. At any rate, in C++, this physically changes the value of name. In Java, what happens is an entirely new object gets allocated, and you're given a pointer to a new string object. We'll get to memory management shortly, but just for the time being, if you do this same thing, now I'll just capitalize it in Java, what happens is that the object, Brad, no longer has a pointer to it. A new object is created with the string nils. You are given a pointer to that. So in fact, we'll see that there are no stack allocated objects in Java. Everything comes off of the heap. So actually, when you declare something to be of some class type, you actually are pointing always to an object. It's never a stack allocated object. Okay, so the first thing, it's immutable. You can't change it. In C++, I could also say something like name2 equals the character m, and that would change nils to nems. You can't do that in Java. In fact, if you want, there's no such a way to treat a string as an array in Java. If you want to get at the character, you would have to say name.char at in the index. So it doesn't even support array notation the way that strings do in C++. You would have to use the char at function in order to get at individual characters in a string. Okay, so the first two differences, strings are immutable in Java. Two, if you want to get at individual characters, you use the char at function. Third difference, when you are comparing strings in C++, the developers of C++ overloaded the relational operators so that you could use less than, greater than, equal, equal. Java's developers did not do that. If you try to compare two strings using relational operators, you will be comparing pointer addresses. It will have so the result will be completely dependent on the two's addresses in memory. It will have nothing to do with the strings. If you want to compare strings, these are the two methods you need to use. So if all you care about is equality, you use the equals method. Okay? This leads us to another thing. The equals method returns a Boolean. For those of you who have gotten used to using ints rather than Booleans in C++, you're finally going to be broken of that habit. Java, when you have a true-false kind of function, it returns a Boolean. You have to use a Boolean value in order to hold that result. So equals returns a Boolean. It does not return an int. You can't go back and forth between a Boolean and int. They're not treated interchangeably the way they are in C++. If you want to instead do some kind of inequality comparison, less than, greater than, use the compare to method. Okay, so here it is. It's an object. You want to ask, well, in that case, you're doing equals. Here's the compare to. So you're comparing A and B. If A is less than B, it will return a number less than 0. If A is equal to B, it will return 0. If A is greater than B, it will return an integer greater than 0. So compares to returns an integer, but equals returns a Boolean. Make sure you use those two functions. It is so easy to fall into the trap of using relational operators. And I forget, I didn't try it before class. I'm not sure whether Java will give you an error message or not if you use relational operators on the strings, or whether it will simply compile and then give you a garbage result. Okay, so questions about that. Those are three key differences. Immutability, use char at to get characters, use equals and compare to compare strings. Don't use the relational operators. Okay, if you want to do in-place modification of strings, and sometimes you do because creating a new string from scratch each time can effectively change an order n operation to an order n squared operation if you do n operations on it. Okay, so that's pretty inefficient. So if you really do want to do mutations to a string, use the string builder or string buffer classes. So for singly threaded applications, you would use string builder. For multiply threaded class applications, you would use string buffer. String buffer just has locking in place to prevent race conditions. String builder doesn't. Okay, they support the same API. It's just that string buffer will cost you more time if you use it in a single threaded application. Okay, so concatenation, you don't need to use the string builder class unless you're adding one character at a time. If you're adding one character at a time and building up a string, use the string builder class. If you just want to concatenate two different strings together, then it's fine to use the plus operator, which operates just like it does in C++. It's a concatenation operator. Okay, but it will create a new string. Okay, questions about strings? I'll let you look up the book has plenty of sections that talk about some of the methods you can use with strings. Feel free, rather than bore you with that, just look them up in the API when you need to. If you need to do a substring, if you need to find the location of a substring in a string, look it up. Okay, it's not worth wasting your time in class on it. Okay, we good with that? Yes. Using a what? Is there necessarily a case where not equals would be better to use the not compared to? I think if all you care about is equality, I believe that equals is supposed to be faster. Okay, so if all you care about is whether they're equal, use equals, because it's supposed to be, I believe, just a tad faster for some reason. Other questions? Okay. Another thing that could bite you a little bit in Java is stricter on its types system. So C++ is pretty loosey-goosey with types. So for example, if I have int x equals 6.3 and I compile that in C++, at best I'll get a warning. And it will simply, what will assign to x? 6. Okay, you pull this in Java, you will get an error message. It will not compile this. And the reason is it's a loss of precision. Loss of precision. This is a pretty important concept in Java. If by assigning something on the right-hand side to something on the left-hand side, you would lose precision, you would lose information, Java will not compile it. It will give you an error message. Okay, the obvious one is a floating point operation. Okay, you can go the opposite way. So if I say double d equals 6, that's not a problem because there's no loss of information when I convert an integer to a floating point number. I don't lose any information when I do that. Okay? Yes? So you couldn't do a float equal to a double? Correct. So if I tried to say float x, very good, double y, then if I try to say x equals y, that's an error. But y equals x is okay. Because when I assign the float to the double, there's no loss of precision. But when I try to assign y to x, there's a loss. Okay, it would be the same thing. If I had short x int y, y equals x is fine. But x equals y, even if it could be represented, not okay. So you might say, but I know for a fact that whatever goes into y is less than, can be represented in the short. If you know that for a fact, you can do a cast. This, okay, tells Java that you think it's okay. And in that case, Java will go ahead and it will do the cast all hunky-dory, yes.
Can you force Java to do loss of precision when casting, or will it still not let you like cast from a bigger one to a smaller, like a double tween?
No, this is doing it. This is what I'm saying is
It will let you do that?
it will let you do that. Now, I'm not exactly sure what happens if you lie in this case. I'm guessing that what's going to happen is it's going to chop the top 16 bits or something, and you will have some loss of precision. Now, there's a caveat. This was on basic types, primitive types, okay? Java applies the same rule when we get to objects, okay? So I know we haven't gotten there yet, but at the top of the C++ hierarchy is a top-level generic class called object. Everything is a subclass of that. Okay, so I might have something like class A, and implicitly extends object, and it might have like a method int get x. Okay, and I might have object B. Okay, I am allowed to say that B equals A. The reason I'm allowed to say B equals A is more general. There's no loss of precision when I am going from A to B. B can represent any kind of object. So that's okay. This is not. Okay, error. Can anyone tell me why Java might not like this particular statement? Yes.
B is not a subset of A, but A is a subset of B.
Very good. So effectively, what we have is that, I'll put it a little less mathematically. So let's say that we had a class C, and it had int get y. So before I said A equals B, so let's say I say B equals C, A equals B. What did I just effectively do? Just assign C, an object of type C, to an object of type A. Does C support the getX function? No. Okay? So the problem is that you can assign a lot of stuff to B, okay, that has no relationship to anything in A. Now, again, you can tell Java, you can do a downcast. Same thing that you were saying. What happens if I try to force it? Java will put a runtime check here. It won't take your word for it. It will compile it, but the compiler inserts a runtime check. It wants to verify that when you do that downcast, that in fact you are assigning something compatible with A to it. It doesn't have to be an object of type A. It could be something that is a subclass of A. But it will perform a runtime check. If it finds out that what B contains is an object of type C, it will throw a runtime exception. So there is runtime type checking going on there. And unlike C++, every object in Java carries type information with it. So you can dynamically query an object and find out what type it is, unlike in C++. Okay? So Java, again, is fine if an assignment does not entail a loss of precision. It will compile it without a warning. But if an assignment involves a perceived loss of precision, then it will throw an error message. Okay, And you can get around the error message by downcasting, but if you're downcasting with objects, Java will put a runtime type conversion. This term, narrowing, you may not have heard it, but you will hear it in the Java community. You've probably, I'm just curious, how many of you have heard of the word downcasting, that when you cast something is a downcast? Okay, some of you have. So downcasting seems to be more of a C++ term. Narrowing is often the term used in the Java community. So narrowing equals a downcast. Okay, it's a loss of precision. Okay, questions about that? Okay, and then that's what I was talking about. Each object carries with it information. You can use the instance of operation to test whether an object is of a specific class. Okay, so, and it will return true if it's an instance of that class or if the class is an ancestor and is a superclass in the inheritance hierarchy. Okay, so here we're saying B is an instance of a, let's see. B is a stack. Stack is a subclass of linked list. And by default, if linked list isn't declared to be of any type, it is of type object. Therefore, all three of these statements would return true. Okay, so if you're ever in doubt, you can always ask instance of. Effectively, that's what the Java runtime check is when you try to downcast. Okay, questions about that? Okay. In that case, let's move on to arrays. And this is where it would help to perk up your ears, because this is the first thing that really gets me questions on Piazza or gets me students coming into office hours and wondering what's going on. In Java, arrays are objects. They're not primitive types. And furthermore, arrays are allocated off the heap. They are not stack allocated. So they must be explicitly allocated using the new operator. And when you declare an array, notice you never give it the number of elements because the arrays are allocated off the heap, which means you can change the size of the arrays that a variable is pointing to. You will see both kinds of notation. You can put the empty square braces either after the variable name or before the variable name. Different companies will have different style guidelines. I don't care which one you use. Either way is valid. Okay, but it is not valid to give a number in there. So the way then you allocate arrays is with the new operator, and that looks just like C++. You're also allowed to do C++ style initialization. The book refers to these as perfect size arrays because they hold exactly the number of elements they're initialized with. So this creates an array with 5 elements and actually assigns the strings Monday, Tuesday, Wednesday, Thursday, and Friday to those 5 elements. However, this is a big one. This is right here. This is what is going to almost always gets me something on homework assignments. After you declare and assign this array object, you do not, in C++, you would have an array of 10 string objects. You do not have an array of 10 string objects in Java. You have an array of 10 pointers to strings. This gives you an array of 10 string pointers. They're all initialized to null. You do not have 10 string objects. If you want to assign them to the empty string, you then have to have an initialization loop that looks like that. Okay, with an array, it carries its size information. So using dot length, you can get the size of the array. And you have to explicitly assign the empty string to it. Otherwise, it will be null. Okay? Now, this isn't such a big deal with strings because typically you would end up assigning strings and it's no big deal. This is where it becomes a big deal on the homework assignment. You have something like stack x equals, stack x equals new stack 10. And then someone says x of 3 dot push something, say 10. And it crashes. Why do you think that crashes? Pardon? Because, very good, because when this statement returns, you don't have 10 stack objects. You have null pointers. Whoops, not zeros. You have null, null, null. So when you try to go through x of 3, it throws a runtime exception because you're trying to do an access through a null pointer. You have to do the same thing. You'd have to go through, and before you do anything, you would have to say new stack. Because you don't get them otherwise. Okay, so this just bites you at the beginning. The fact that when you allocate an array of objects, you only get pointers. You do not get the objects themselves like you would in C++. Okay, so many students have no issue with the fact that there's no stack allocated objects, but then they don't realize that applies here too, that when you say new stack 10, all you're getting is an array of pointers. You're not getting an array of objects. We good with that? We got questions? Yes. Yeah, there should be. Thank you. I like to put my brackets there. Thank you. I'll get that fixed. That was a recent change I made. Thank you. Other questions? Okay, so that is the big thing to know about with arrays. Multidimensional arrays look just like they do in C++. So if it's a primitive type, you're good. You say new int 4, 5, you'll have a 4x5 int array. You can also use this notation so that you get an array that has 4 rows, but then each row has an indeterminate number of columns. Okay. You can leave the last, this works with 3-dimensional, 4-dimensional, 5-dimensional arrays. You can leave the last one blank. You can't leave more than one blank. So you couldn't say, for example, int b equals new. That's no good because the compiler has absolutely zero idea how many, sorry, this should be new int, has absolutely no idea how many ints to allocate. So you're only allowed to leave the last dimension unspecified. No matter how many dimensions you have, you only are allowed to leave the last dimension unspecified. Okay. Finally, I encourage you to get used to this nifty array construct, which is also available from the C++ standard template library. Allows you to iterate through vectors. So it's a new type of for loop that allows you to iterate through the elements of an array. And what it does here, this is the name of the array. Okay. And name of variable to hold elements of array. You must declare it there. You actually can't declare it outside of the for loop. You'll get an error message. I don't know why, but it is what it is. That variable is scope is limited to the lifetime of the loop. Once out of the loop, that variable goes out of scope. It just, for whatever reason, you have to declare it in the for statement. And it doesn't give you the index values. It gives you the values of the array. So here, what would be returned, the first value you would get would be 32. So element would first be set to 32, then to 87, then to 3. So you're not getting the index values. If you need the index values, you have to use a traditional for loop. But if all you care about is the values themselves, then this is a very succinct way of writing it. It avoids running over the end of the array, so it's a lot less prone to bugs. Okay, if you want to modify the elements of the array, you cannot use this. This is read-only. Okay, you can assign values. You could assign a value to element, but it would not change the element in the array. So it's only good for reading. It's not good for changing values in the array. If you want to change values in the array, you also have to use a for loop. But you should try to get used to using this type of for loop. It's pretty idiomatic in C++. Java, yes.
So when you were iterating over two-dimensional arrays,
Mm-hmm.
I guess the element would be a one-dimensional array?
Correct. Yes. Very good. So then you would get, it would have to be for int element colon multi. And then you could actually write a inner loop that would say for int, say, e element, if you wanted. Questions about that style of loop? It's just, it's nice, like I say, when you are just running through an array and you only need the array values, I strongly recommend you use it because you're no longer susceptible to out of bounds by one errors. Okay, in fact, no one even caught it. Did it? It's less than, if it's one. No, this is right. Names less than length is right. Okay. But for example, if you accidentally wrote I less than or equal to names.length here, you would get an exception, which you couldn't get with the for loop. Okay. So that's arrays. Now let's talk about enumerated types. So Java gives us a very simple way to use enumerated types. So I'm going straight to the, so in Java, just like in C++, there is a enumerated type facility. Here's a very simple one. I create a type called day, and it has the 7 constants you see there. By default, you should capitalize the constants. Okay, it's a style thing. What this does in Java is it actually creates a class called, effectively it creates a class called day. And it then creates effectively 7 instances, one for each of the constants. Okay, now this is all going on behind the scenes. When you print them out, so when you print out a enumerated constant in C++, what does it print? Does anyone know? If you have an enumerated constant in C++, do you even know what values are assigned to enumerated constants in C++? They start with 0. So when you print an enumerated constant in C++, it prints its integer value, which isn't very informative. If you print if I have now I can declare it day, let's say my day, and I say day dot Wednesday, oh, that's too long, Sunday. And I now try to print my day, you would print it as a string, and it will actually print out Sunday. It won't print out 0, which is very handy. Okay? When you assign constants like this, you have to prefix it with the type name. It's not smart enough. If you do this, it will assume Sunday is a variable name and you will get an error message. So when you assign enumerated constants, you need to prefix the constant with the type. Anyone have an idea why that might be the case? Actually, that's going to be a little deep. The reason is effectively you're getting a pointer. Okay? You're allowed to have another public enum. What if I have public enum weekend? And I also have Saturday and Sunday. Okay? So then if I just said equals Sunday, well, what should it be getting? Who knows? So what you're really getting is a pointer, and that's why you have to prefix the enumerated type with its type name. So it's nice because once you assign or declare something to be of a enumerated type, you can't make typos. So sometimes people would say, okay, I could just as easily have strings and just say like string my day equals, see the problem? What if I make a typo? Not only that, strings, well, you always are using new string objects. You could also use constants, but again, you could have the same problem, which is I could use constants for days like 0, 1, 2, 3, 4, 5, and again, I might inadvertently assign a bad value. Might say, there's no restriction then on saying still, I might say int my day, and I think I'm bored, I'll just assign it 7, forgetting that the constants go from 0 to 6. It would get the value 7, bad value. So enumerated constants are a nice way of both providing useful documentation in your code and also preventing bad values from being assigned to a variable. But Java's, okay, now look at this. So we have day, day, switch. Why don't, he's just saying, wait a minute. Dr. van der Zanden said I had to prefix it with the name of the type. There's the case statement, no type. Why? Well, you're close. It knows the type at this point because we switched on day and it knows that day is of type day. So in a case statement, when the type is known like that, it doesn't. I don't like that, but if you read the tutorial, I just wanted to explain why in a case statement it's not being prefixed with day dot. Okay, but there's so much more. So what you can do is, because these enumerated constants are objects, you can actually assign values to them, which is handy sometimes. My area is graphical user interfaces, and we use enumerated constants a fair amount for things like font sizes. We might have an enumerated type for a font size, okay, and we might have small, medium, and large. Well, that's not of much value when we actually go to display it. It needs to know an integer for the font size. So we might have small as 9, medium as 12, large as 20. Or I might have font name or font, and then I might have like Times Roman. But in fact, that again doesn't give the Java system any information, so I would actually have to have a string, have it storing a constant. So what we can do with each of our enumerated values is we can store some information with them. Here we have the planets, and they're storing the, I believe, the mass and the radius of each of the planets. Okay, so these enumerated constants can actually come with values, and since they're actually objects, here we can store, so they have to be declared as finals. You're not supposed to be changing their values. The mass of mercury isn't supposed to vary. Okay, so they're generally supposed to be declared as private final. We will get to this, but the way you declare things to be constants is with the final keyword, not const. For some reason, Java didn't use const. They decided final would be the way you declared a constant. So if you want to declare a constant, use the word final. Okay? And then you can see here each of the constants was given some values. So we have a constructor that assigns values to those constants. And then we even have some functions that you can call that will return those values. And we actually declared some convenience functions that would allow us to compute things like the surface gravity and the surface weight of these planets. So when we actually end up declaring these things, we can, in this case, we can also iterate through the enumerated constants using the values function. So you can actually get an array of all the values associated with an enumerated type using the dot values that returns an array of all of the instance objects. And then notice here, %s is being used with p. So when we want to print out a constant, we print it using %s. And then we also are printing out its weight with %f, and we're getting that by calling its surface weight function. We're passing in not its mass. I think what we're trying to do is figure out what is the weight. Let's see, I forgot to look at it. The mass is actually coming here. It's coming from that value. So it's taking earth weight. I'm not a good scientist. So I think it's taking your weight here on Earth and figuring out your weight on another planet is what it's doing. Yep. So it's figuring out what is your mass here on Earth, and then it's telling you what your weight would be on each of the other planets by passing in your mass. Okay. Yes.
Just wanted to mention that force is mass times acceleration, and weight is a force. So basically, they're just taking the force, dividing it by the acceleration of gravity to get mass.
Okay. Gotcha. Okay. Thank you. That is, so quick side story. I went into college in engineering. First semester I had to take chemistry and economics. I was not good at chemistry. I butchered every lab. The lab TA told me that if I spent as much time at office hours with the labs as I did with the homework assignment, that I would do just as well on the labs as I was doing on the homework assignments. Because on the homework assignments I was getting A's, and I think on the labs I was getting a charitable C. And I had to shamefacedly tell my lab instructor that I in fact did spend more time at office hours with the labs. It's just she wasn't there during those particular office hours. But it would be like you weigh this, piece of mineral. I would weigh it 5 different times, and each time it'd be off by a tenth. The measurements would be a tenth of a ounce different, and you were supposed to get it to like a thousandth or something, and it was a tenth of an ounce different. It's like, come on, I'd just be sitting there so frustrated. So, economics, it was great. Everything made sense. Next quarter, Brad's in the business school. No science for Brad. So, I did take all the remaining science classes by examination. Thank you very much. Didn't have to take any more of those awful lab courses. So at any rate, don't be planning on any science problems in your homework. There we go. So that is me and my science phobia. Okay. Any rate, bottom line with enumerated types. They're a lot more powerful than they are in C++. In C++, they're just integer constants. In Java, enumerated types are actually instances of objects. Those instances can store values that are of use to you in the program. Okay? So, as I said, I could assign actual point sizes to fonts. With the planets, we could assign their mass and radius, and then you can extract that information from the constants to do useful computational work with them. But if all you care about, you don't have to go to all that complication. You could simply declare, in its simplest form, you simply declare it like that, and then you can declare values. Normally, you put this in a separate file, unless you use it in only one class. In that case, you could embed it in the class. Okay, because it does create a class. So typically you put your enumerated, you would put this in a file named day.java, and then it would compile, and it would create a .class file for it. Okay, if you only use that enumerated type in one class, then just make it a nested type within that class. But otherwise, put it in a separate file. Okay, questions about enumerated types? Okay, that brings us to the last subject for today. And that is, I made you read through Chapter 8, I believe. Is it 8 or 9? I think it was 8. Memory management. So, this cannot be emphasized enough. Java eliminates stack allocated objects. All objects are allocated off the heap. Strings, arrays. Any object comes off the heap. There is no stack allocated objects. You're wondering, what does Brad mean by stack allocated? In C++, you can write stack S or you can write stack S equals new stack. Those are two very different things in C++. This first one in C++, the object is allocated on the stack. Remember, in C++ you have a stack for every function, a frame for every function. There would be an object of type stack for S allocated in the stack frame for main with this declaration right here. Whereas if this was foo, and this had stack asterisk S, this would be a pointer to an object that came off of the heap. So in Java, when you declare something to be stack S, what you get on the stack is a pointer, a 4 or 8 byte pointer. It's a pointer, and initially that pointer is null. So there is no stack allocated objects in Java. Okay? Java has no explicit pointers. Everything is a pointer. Implicitly, everything that is not a primitive type is a pointer. It is a pointer to something on the heap. Okay? You still use new to get an object off the heap. It is just like C++ in getting objects off the heap. You use the new operator. But unlike C++, you never call delete. So you do not have memory reclamation in Java. All you have is garbage collection. The garbage collector takes care of your heap allocated objects. When there are no longer, when there are no longer pointers to, come on. There we go. When there's no longer pointers to an object, the garbage collector reclaims memory. No more memory leaks. No more premature deallocation of objects leading to dangling pointers. Java cleared up. This, in my opinion, is the single biggest contribution of Java. Is it got rid of the only time anymore you are going to essentially get a seg fault is when you go through a null pointer. And it will immediately throw an exception that says it's a null pointer. You will not have dangling pointers anymore. You can't prematurely deallocate something. There's still a pointer to it. It still exists. Similarly, you don't really have memory leaks. Oh, wait a minute. I just said that again. Okay, that's false. They say you don't have memory leaks. Garbage collection is never perfect. Okay? So, in fact, garbage collectors don't always get rid of stuff that could be garbage collected. So over a long-running program, Java programs tend to bloat up because actually they do tend to spring memory leaks. Fortunately, it's not your, well, I shouldn't say it's not your fault either. If you just go start saying new all the time, it is your fault. If with strings, you add characters one at a time using the concatenation operator rather than using the string builder class, it's your fault. Okay, so you still have to be careful with memory. Okay, because you have no explicit pointers, you don't have pointer arithmetic. Yay. Okay, I know Dr. Planck went like that, but P++, P minus doesn't work anymore. Okay, so the last thing today let's just talk quickly about garbage collection. How is it done? Okay, so there's essentially two ways that garbage collection is done. Actually, did we not? Gosh, all the way back here. Okay, so there's two basic ways to do it. Reference counting, something called trace collection. Okay, reference counting, what you do is you keep track of the number of pointers to each object. So down here, I have string A equals new string hello. So at that point, hello has one reference to it. Next, I allocate world, and now world has one reference to it. Now I assign A to B. That means that the pointer to hello is assigned to B, which means that hello now has two pointers to it, A and B, but world has no pointers to it. So its reference count is 0, and it can be garbage collected. So reference counting is very simple. Every time you assign a pointer to something, you increment its reference count by 1. Every time you remove a reference to something, you decrement its reference count by 1. When the reference count goes to 0, you garbage collect it. Okay? Each memory block typically contains a 4-byte field that contains the reference count. It may also contain some other information. Also, you have to instrument your pointer assignment. So every pointer assignment requires that you increment the reference count for the memory block you're pointing to. And if you are removing as a result of that assignment a reference, like here, you're removing a reference to world, you must also decrement a reference count. So that means every pointer assignment goes from potentially being 1 assignment to potentially being 3 operations. But it's a very simple, so its advantages, it's simple, it works well for strings. The cost is uniformly distributed over the program's execution, so you don't get annoying pauses. Basically, when a reference count goes to 0, you garbage collect the object. You return it to the heap. Disadvantages. Doesn't work well for circular structures. What's the problem with a circular structure? Yes?
One refers to the other, and then so both of them have something referring to them?
Exactly. Everything in a circular structure has a reference count of 1. Even if nothing refers to that circular list. Let's say you have a circular list. Every node on the list has a reference count of 1. Let's say you no longer have any outside pointers to that list. It can't be garbage collected because every node has a reference count of 1. Hence, memory leak. Okay, so that's a disadvantage of reference counting. Basically, circular structures will lead to memory leaks. And you have to add reference counting before and after every pointer assignment. This form of reference counting is really not typically used in garbage collectors. Okay, it's too primitive, too rudimentary. What is normally used is, well, the other thing with pointers and reference counts is you need some kind of, well, that just shows circular lists. Okay, I won't worry more about reference counting. Let me now move to what's called trace collectors, and there's 3 types. Mark sweep, there is generational, and what is the third one? Have it in my notes. Mark and sweep, stop and copy. Okay, stop and copy. The general idea with all tracing collectors is this. So I'll go back here. No, I want to go back to PowerPoint. Thank you. Can you see it? No, you can't. Hello? There we go. Okay, so let's actually go. All three tracing algorithms are going to do the following. Basically, you have your stack with your frames, main, A, B, C. Okay, they have pointers to things on the heap. Those things on the heap may also have pointers. So what happens with generally the tracing is that when you run out of memory, it needs to garbage collect. It needs to compact memory and deallocate anything that can no longer be accessed. What it does, the tracing collectors, is it goes through the stack. For every pointer in the stack, what it does is it starts a depth first search. Every object it reaches is still in use. Okay, so it marks every object that it reaches as being in use. And notice you have to descend through all the pointers in each object. So tracing collectors require what are called strongly typed language, meaning you have to be able to know the type of the object because you have to know where the pointers are in the object. When you hit a memory block, it's not enough to say, oh, this memory block is in use. That memory block may itself contain pointers like next and previous that you need to chase. So the memory block really needs to carry type information with it so that the garbage collector knows the type, knows where to find the pointers, and can chase them. Okay? So generally, tracing collectors do something like they also will mark stuff, everything perhaps first as unused. Okay, and obviously, as it chases pointers, it's going to mark them as used. So this is really just like it is depth first search. At the end, it has a set of unused memory blocks and a set of used memory blocks. So again, the garbage collector makes a pass through memory. It finds all the unused blocks, the blocks still marked unused, and it deallocates them by returning them to the garbage collector. This works great with circular data structures. Okay, this one is still all of the nodes are marked unused because there was no external pointer into that circular list. So tracing collectors are able to garbage collect circular lists, unlike reference counting schemes. Okay, so basically tracing collectors essentially are depth first search engines. They are starting, it's basically for each pointer on the stack, depth first search that pointer and mark all memory blocks that are reached as used, and then at the end, garbage collect any unused memory blocks. Very simple. Okay, works very well. Okay, so first one, that's exactly what happens. It's called mark and sweep. Walk through the heap, mark every block as useless, do a depth first search for each pointer outside the heap, meaning from the stack, mark all blocks reached as useful, do a final walk through the heap, and remove or move every block marked useless to the free list. Simple enough. Less overhead than reference counting because you don't need to instrument every pointer assignment. You don't need to keep the reference counts. You can garbage collect circular structures. Disadvantages, it can cause long pauses because you normally only garbage collect when you run out of memory. Most machines have a lot of memory, so you end up with long pauses. You need a strongly typed language, although most languages these days are strongly typed. Okay, so even scripting languages, the values carry their types with them. You know the type. Implementation can be a little tricky. The reason it can be tricky, I know I'm almost out of time, is you perform this garbage collection when you're out of memory. So where does the useless fields come from? How do you handle the depth first search? Because the depth first search itself needs a stack. Okay, so the problem is you're doing this implementation when you're already out of memory. So it's not as easy as it sounds. And memory fragmentation, the memory, where you get the memory is here, there, and the like. So you may be garbage collecting a bunch of smaller fragments, but you may end up in your heap with a little fragment there that can be used, but now this whole bunch is used. Now this is unused. Maybe this is, this is used, this is unused. So you're fragmenting. At some point, you may not have big enough blocks to allocate bigger objects. So memory fragmentation is a problem. Okay, to wrap up, the implementation, I'm not going to go into it. I'm not going to hold you responsible. They usually reverse pointers. As they're doing the depth first search, what they normally do is to save space, rather than keeping a stack, they simply reverse the pointer. So when you go from here to here, they just reverse the pointer. When you go from previous to here, they simply reverse the pointer so they can get back efficiently, rather than having to build up stack frames like you would normally with depth first search. They just reverse the pointers so you can get back. But this makes it tricky to do. Okay, I'm just telling you how garbage collection is done. Will you ever write a garbage collector? Probably not. I just want you to know how garbage collection is performed. I will finish up talking about garbage collection on Thursday, and then we will get to classes and functions in Java. Okay, I know I'm going quickly, but I think most of this material should be pretty familiar with to you. As far as the programming goes. Okay, I will see you all on Thursday. Remember, do the quiz. Okay, it covers the material we talked about today. And also do the pre-class activities.